Thanks, Gershom. Can everyone? Cool. Can everyone hear me okay? Sounds good? Okay, cool. All right. So yeah, this is a gentle introduction to category theory. So just a refresher, how many people here know what a monoid is? Okay, cool, lots of people. So for those of you who don't, just a quick refresher. A monoid is just a set or a type, depending on whether you're a mathematician or a computer scientist. I'm going to use sets because I'm the former. A monoid is a set M together with an operation that takes two m's and returns another m, which we call multiplication. An element called the identity, which I'm just going to write with this little 1 sub m. And it's got a couple of laws that it has to satisfy. For instance, if you multiply anything by the identity, you get back what you started with. And it's associative, so if you multiply two things and then another thing, it's the same as if you multiply the right two things and then multiply the left guy by that. Right? No. Groups have inverses. They are semigroups. They're semigroups with identity. So lots of things are monoids. Lists, for example, everyone's favorite, where multiplication is concatenation and the identity is the empty list. Numbers, if you add two numbers, you get another number, and the identity is 0. Numbers again, where now multiplication is actual multiplication, and the identity is actually 1. Functions from a set to itself, where the multiplication is composition, and the identity is the identity function. And the list goes on and on and on. So I'm going to give an example of something that's almost a monoid but not quite, which is if you look at all matrices and the operation is multiplication. So can anyone tell me what the product of these two matrices is? The correct answer is no, you cannot. So you can only form the product of two matrices if the number of columns of the first guy is the number of rows of the second guy. That's just, first linear algebra class anyone takes. But it's sort of got a lot of other nice properties that monoids have. You have, well, maybe not a single identity matrix, but you've got a family of identity matrices, and each one works like an identity. If you multiply something with it and it's well defined, then you get back what you started with. And if you have A, B, and B, C are both well-defined products, then it's associative. So if you only look at the set of n by n matrices for a fixed n, then they do form a monoid under multiplication because the number of rows is always the number of columns. It's great. So this is really trying hard to be a monoid, but it's not quite. So can we do any better than this? And the answer is yes, we can. So it turns out that if you take all of the matrices, all of them, they form something called a category. And that categories give us exactly what you were looking for, where you have a multiplication operation that satisfies the monoid laws, substantially weakened, but your multiplication is only defined when you've got a certain coherence condition, when you can't have you can't have a mismatch in type, I guess. So I'm going to be talking about category theory, and so just a brief outline. I'm going to define categories and give millions of examples. I'm going to define functors, which you probably know from Haskell, but I'm going to define something a bit more general. I'm going to define natural transformations, which you may or may not know from Haskell, but I'm going to tell you what they are in Haskell. And then I'm going to talk about something called the Oneida lemma, which is kind of one of the most deep and interesting trivial results in category theory. All right, so let's start with categories. It's called category theory, so we should probably talk about categories. Oh, by the way, if anyone has any questions at any point, feel free to ask. This is a gentle introduction after all, so All right, so a category. What is a category? Well, so first you've got a collection of these things called objects. And these have nothing to do with object-oriented programming objects. They're just, you can think of them almost kind of like nodes in a graph. So, you know, we have a collection of objects and we'll use capital letters to mention them. And we use this little set element notation to say, you know, A is an object of C for some category C. So now the interesting bit is, given two objects, you have a collection of morphisms that go from one object to the other. So and we usually use lowercase letters that start with F for this. So usually we'll notate it using F colon A arrow B, kind of like you'd see in Haskell. Say F is a morphism that goes from A to B. Sometimes people use this notation, especially when they're drawing bigger connections of these things. And these both mean that F is just a morphism from A to B. All right. That's not all. You also have, for every object, an identity morphism. So this is just, it goes from an object to itself. And given two morphisms, one from A to B and one from B to C, you can compose them. Kind of like functions, you might think. Now, there are a couple of laws, just like with monoids. Yeah. It can be, but it doesn't have to be. I'm going to gloss over that a little bit. You can think of it as a set, but it might be very, very large. Yes. Yes, I will give some examples of categories which have morphisms that aren't functions. So, but first I need to tell you what the rules are. So just like with monoids, there are two laws. There's the identity law, where if you compose with an identity, you get back what you started with. And there's the associative law, which says, you know, if you form this composite, it doesn't matter sort of where you put the parentheses in this operation. So one way that you get these categories in practice is by looking at what I call categories of things. And this is not an official term, this is just something I made up. So you've got some kind of structure that you're interested in. Maybe they're sets, maybe they're some other weird collection thing you're looking at. And you've got rules about how this thing behaves. Then you can talk about a category of all of these structures, where the objects are the structures themselves and the morphisms are sort of structure-preserving functions in some sense. So I'm going to go into some detail about some examples of what this stuff means. So first let's start with one everyone's familiar with, types. So there's a category of Haskell types where the morphisms are just Haskell functions. You get identity maps. So given any type A, you've got a map from A to A, which is just identity. And you can compose. It turns out that Haskell is kind of special. You can define composition within Haskell. But yeah, it's pretty straightforward. Everyone knows about this. And you can check that these laws hold yourself. It's pretty easy. Yes?
So is any function with a given type structure a morphism between those types?
Yes. So kind of in a similar vein, this is sort of, you know, the mathematicians version of Hask. There's a category set where the objects are just sets and the morphisms are functions. The identities are identity functions, composition is composition, and it's pretty easy to check that the laws hold. So now let's go to a category that's neither of these things. It's a bit different. The category of monoids. So here we've got monoids are the objects, so anything that has multiplication and identity and obeys the laws. So the morphisms between a monoid M and a monoid N are called monoid homomorphisms. And they're functions that take the identity to the identity and that take multiplication in M to multiplication in N. So it sort of preserves both identity and multiplication, if that makes sense. So identities and compositions It works very much like identities and compositions in the family of sets. The identity function preserves the unit, and it preserves multiplication because x times y is x times y. And compositions of homomorphisms is in fact a homomorphism. And the category laws follow from the same laws for set. Yeah.
So when you say it preserves the unit and also the composition, it preserves the structure?
Yes, it preserves the structure of the monoid. So in a similar-ish vein, there is a category of vector spaces, and the mathematicians in the crowd are going to look at me funny for this definition because it's not quite right. But I'm going to say that the category consists of objects are the real vector spaces, just r to the n, n-dimensional vectors. The morphisms are matrices. This might start to sound familiar. The identity on Rn is just the n by n identity matrix. And if I've got a n by m matrix and a k by n matrix, I can multiply them because, the number of whatever is the number of rows equals the number of columns, or I've probably gotten that backwards. But the composite is defined as the product. So, hey, problem solved. We have matrix multiplication. And, since you can prove the identity and associative laws for matrix multiplication, you can prove them for this. So the other kind of category that oftentimes comes up in sort of day-to-day playing with categories is, some people like doing it, is when you have some kind of structure that you're already familiar with, and you can re-envision it as a category. And how this takes place depends a lot on what kind of structure you started with. So first, every set can be turned into a category. This is something called the discrete category, and you'll soon see why. So the objects are just the elements, and there aren't really any interesting morphisms. It's just identities. You just have a morphism from x to y if x and y are the same thing. The identities are the identities, and composition of identities is identity. You can prove the laws very easily. So yeah, it's a category. It's not a very interesting category. There's no real morphisms to speak of, but it's a category in and of itself, and it's worth talking about sometimes. So now, let's say that you have a graph. So like, you've got vertices and you've got edges. Maybe it's got multiple edges going from one vertex to another, or maybe you've got loops or something crazy like that. But you don't have to. But no matter what, you can create a category which is the free category on the graph. So the objects, as you might guess, are the vertices of G. Now you might think the morphisms should be the edges in G because, well, I've used the vertices, so now I need to use the edges. And it's almost right, but not quite. The morphisms are actually paths. So, given a point x and a point y, I have, the morphisms from x to y are all of the ways I can sort of get from x to y by following a sequence of edges, possibly an empty sequence. Speaking of the empty sequence, the identity morphism is just a constant path. It just starts at a vertex and stays there and ends there. And given two paths, I can concatenate them. So I've got a path from u to v, and I've got a path from v to u. I can follow one and then the other, and I get from u to w. Yeah, it's a DFA. And proving the identity and associative laws are easy. So now there's sort of one more kind of interesting example where, in particular in that example, the morphisms weren't really functions. Like the vertices of a graph don't have any internal structure. There's no way of like mapping from one vertex to another really. So they don't have to be functions, but they can be, and they can represent functions, but they're not always. So if I've got a monoid, then I can turn it into a category, and it's kind of a bit weird how you do this. There's one object, You call it star because there's nothing really exciting about it, and apparently there's nothing exciting about stars, or that's what mathematicians say. So if you look at the morphisms from star to star, you've got one of them for every element of your monoid. The identity on star is just the identity element of your monoid, and composition is multiplication. So this actually shows how categories are a generalization of monoids. So when you have a monoid, if you've got any two morphisms or any two elements of the monoid, you can compose or multiply them together. You can put them together. A category is sort of like, well, you know, maybe you've got some sort of like different, you know, you have a coherence condition that says these things can, only these things can be put together. But if there's only one object, any morphism can compose with any other morphism. So, you know, categories with one object are monoids, and monoids are categories with one object. I'm going to be sort of going back and forth across that isomorphism silently a couple times during this talk. Identity and associativity are just from the laws, the monoid laws. All right, so now on to functors. So we've got a bunch of categories that we've sort of created out of thin air. It's natural to ask how you can relate these categories to each other. So kind of like how you have, I define monoid homomorphisms, or morphisms between monoids that preserve the monoid structure. We'd like to have some kind of category-ness preserving map that goes from one category C to another category D. So, you know, what should it be? Well, it ought to do something sensible with objects and morphisms, and it ought to preserve identity and composition. You know, if we're going to call it, you know, structure preserving, it ought to preserve the structure. So we define a functor. So given any two categories, I can define a functor as a map from C to D, and here's what it does. Given an object in C, I get an object in D. Given a morphism in C, I get a morphism in D. And furthermore, you know, if the morphism goes from X to Y, the new morphism goes from f of X to f of Y. I've got a couple of laws. It needs to preserve identities. So if I take the identity morphism from X to X, it goes to something from f of X to f of X, it should be the identity. And if I compose two morphisms in C and then take f of that composite, it should be the same as if I take f of the individual morphisms and then compose them in D. So you can think of this as sort of like a way of translating the notions in category C into notions in category D. So let's go through some simple examples. So first, the ones that everyone's familiar with. So a functor going from the category Hask to the category Hask is just something that obeys, that's an instance of functor and obeys the laws. So, you know, the list functor, the maybe functor, reader R, all of these are functors that go from Haskell to itself. So what does it do with objects? Well, given a type A, you get the type f of A. It's just, you know, whatever the type constructor is. And the map on morphisms is given by fmap. So you've got a map from A to B, and you get a map from f of A to f of B. Usually you don't see these extra parentheses here, but I put them in there so that you can really see this turns functions into functions, rather than saying, here's a function and a thing, and I put them together and get another thing. Checking that the identity and composition laws hold is, you know, an exercise to the programmer. You know, if you're defining a new functor, you need to make sure that it's, you know, it obeys, you know, if you take identity, it turns into identity, and if you take a composite, it turns into a composite. So let me give some examples of some others. So monoids are sets. And, you know, as some people have mentioned in their questions earlier, you know, monoids are also semigroups and groups are also monoids. So there's sort of like this building up of structure from basic things to more complicated things. So morphisms between monoids are also special kinds of functors. Or, sorry, special kinds of functions. So in particular, you can send the category of monoids to the category of sets by saying, well, I'm just going to forget that M has a multiplication and an identity, and I'm just going to forget that F is special. And it's just, now it's just a set, and now it's just a function. And, you know, it works. It just sends, it follows all of the rules. And so people call things like this forgetful functors for an obvious reason. They forget the structure on M. Now, there's sort of a related notion that unfortunately the relation between that and forgetful I'm not going to get into very much is, so if I have any set, you know, say like, you know, the set of integers maybe, then I can create a monoid of words in S, which are sequences of elements. So, you know, I might have the empty sequence, I might have the sequence 1, 2, 3, I might have 5, 7, 6, 4, -2, whatever. And I multiply sequences by just concatenating them together. This might sound familiar. So you can turn this into a functor going from the category of sets to the category of monoids, where given any function from S to T, we get a homomorphism that sort of says, I've got a sequence of integers. I just apply F to each integer, and then I get a sequence of, well, whatever F returned. So we call f of s the free monoid over S. And this is basically the same as the list functor in Haskell. It takes, you know, you've got some type like int, you turn it into list of int. Now, you know, given a function from int to string, you can map it over the list and get a list of strings, etc. So functors compose. If I've got a functor from one category to another and a functor from this category to another category, now I can get a functor that's the composite. How does that work? Well, you know, on objects you just send it to whatever f sends it to and then send that to g, whatever g sends it to. And morphisms does the same thing. And it preserves all of the laws because the individual parts preserve the laws. You also got, given any category, you can look at an identity functor that goes from the category to itself. It just sends everything to itself. And it sends morphisms to themselves, and it preserves all of the laws because you're just sending things to themselves. Of course it preserves things. It turns out that composition is associative, and that identity is a unit for it. So now that means that we get a category. You know, we have the objects are categories and the morphisms are functors. This is a little bit dangerous. This starts getting into Russell's paradox-like territory, and that's why I was kind of like, yeah, objects of a category are totally can be thought of as sets as long as they're allowed to be big. We already had that problem with set. There's not a set of all sets. That's dangerous. But anyway, size issues aside, everything works out. All right. So now that we've got this category of categories, we can see that those second group of examples I gave when I was talking about categories are actually describing functors. So given a set, I can turn it into a category by taking the discrete category. Given a graph, I can turn it into a category by looking at, you know, sort of the free category. Exercise for the reader. Figure out what the morphisms in the category of graphs should be in order for this to be a functor. It's kind of fun. There's the one object category where you take every monoid and turn it into a category, and monoid homomorphisms turn into functors. All right, so more examples. Everyone loves examples. So let's say I've got a category and I've got some object, let's call it R, standing for either representable or reader, depending on who you ask. Then I can look at all of the morphisms from R to something is a functor that goes from the category C to the category of sets. So let me explain what this means. So I've got an object A. Now, I've also got my object R, so I can look at all of the morphisms from R to A. I send A to that set. And if I've got a morphism from A to B, then, well, if I've got a morphism from R to A, I can turn to a morphism from R to B by composing with F. Right? So this is sort of like, you know, I sort of like have my object R and I look at like all of the ways that you can get out of it. And I send every A to how you can get it from an R. So that's actually just a lot similar to the reader functor in Haskell, except that, you know, reader takes a type and returns another type, whereas this thing can take anything and it'll give you a set. So now I'm gonna, so if you put something into the first slot in HOM, you know, sort of waving our hands a little bit, what happens if you put something into the second slot of HOM? Do you still get a functor? And the answer is sort of, almost, yes. So is it a functor from C to set? So, okay, I can send objects to sets, and I can send morphisms to functions, but if you're looking closely, you might see that something isn't quite right here. So I started with a morphism going from B to A, and I ended up with a morphism going from, you know, the thing for A into the thing for B. I got F turned around. And these sorts of things come up a lot in these things that sort of almost are functors, but they turn things around. So we have a way of dealing with that. So if I've got a category, I can make something called the opposite category. It has all the same objects that C does, except that the morphisms go backwards. So, you know, if I've got, you know, like in the category of sets, for example, if I've got, you know, the set of integers and the set of strings, you know, show would be an example of a function that goes from an integer to a string. In the category set up, there would be a morphism from string to int, which is sort of unshow, or show run backwards in time. It's not a function. It's like some kind of weird relation that is, you know, everything that it hits everything exactly once, but it can sort of send something to multiple places or to nowhere at all. So, you know, again, identity morphisms are just, you take the identity and you op it. And composition, well, if I've got F goes from A to B and G goes from B to C, then this guy will go from A to C. So if I op it, I'll get something from C to A. So F went from A to B, so this guy goes from B to A. And this guy went from B to C, so this guy goes from C to B. So if I compose them, I get something from C to A. So I go C to B to A. So, yes?
So I'm missing something here, but so in C, you do a morphism from A to B, and in C op, you morphism from B to A.
Yes.
But what if like there's not a well, that kind of sounds like an inverse operation.
Yes. it sounds like an inverse operation, which is why COP and C are different categories. So, for example, like if I've got if I've got the empty set, I can, given any other set X, I can define a function from the empty set to X by saying, well, I need to define it on all of its values. I'm done. But, if X is, say like, a set with 5 elements or whatever, if you try to map it back, you're going to run into trouble because where do those 5 elements go? They can't just vanish into the ether. So there aren't any functions from 5 to 0, but there are morphisms from 5 to 0 in set up. So, in particular, another way to think of that is that now, since there aren't any functions from 5 to 0 in set up, there aren't any morphisms from 0 to 5. So it's not really this is sort of the morphisms aren't quite functions. They're just things that you can compose together. So you can't always, so just like you can't always invert a function, you can't always like get something going the other way inside of a particular category. But if you go into the opposite category, you'll get something going the opposite way, but you might not get the thing that you might not get one going the opposite way, if that makes sense. Mm?
Morphisms are generalization of functions.
Yes.
They are mappings that are fixed in place so that when you get the opposite category, you get all the mappings that...
Well, you don't get mappings that are, it's not quite that. It's that morphisms are, to think of them as generalizations of functors, think of it like paths. Like you've got something over here and something over here and something over here, and you can go from here to here to here. And if I now, so given any graph, given any directed graph, I can make a new directed graph which is exactly the same, but the arrows go the opposite way. So now you can't go from U to W in the new graph, but you can go from W to U.
But then you're saying also that it's not important to know, like, if 1, 2, 3 maps to 0, and now we're in the first category, it's not important to know how.
Could I maybe suggest one thing?
Sure.
A morphism is a line with an arrow drawn on it. That is the whole point. That is it. It's one of these things where mathematicians say, well, it's because I defined it that way, now let's see what we can do with it. It doesn't have to mean anything beyond that.
It doesn't necessarily have any internal structure, and neither do the objects. They're like just things. You can't see inside of them. All right. And some people, yes, some people will define categories by calling these things arrows instead of morphisms. That has a little bit of a relation to arrows from the last talk, but it's finicky.
Just like the multiplication in Monoid doesn't have to be defined very well. This is for arrows, like there's no representation, just whatever.
Yeah. Yeah. All right. So if I've got a category and some object H, I get a functor that goes from the opposite category to set. So, okay, so if I've got a morphism from B to A in C, I'll have a morphism going the other way from A to B in C op. So I can send this guy to a function that goes from hom AH to hom BH by saying, well, I've got a function from A to H, and I've got a function from B to A. Now I'll get a function from B to H. So one reason I called this guy H, whereas the last one was R. When I put something in here, I called it R, which stood for reader. Now, when I put something in here, I'm calling it H to stand for handler. So you can think of this as being like handlers that will return H. And so, given you can say, okay, I have a way of handling things of type A. And if I've got a function from B to A, then I can handle things of type B too. But if I've got something from A to B, then I can't turn that into a way of handling B's. So you see these functors that do this reversing arrows thing a lot. So we'll say that if you've got a functor from the opposite category of C to D, we'll call that something called a contravariant functor from C to D. It's a little bit misleading because it's not exactly a functor from C to D, but it's sort of almost up to this direction swapping thing. And similarly, they'll sometimes say that a regular old functor is called covariant. Yes? It means maps. It means it's a function that takes one thing to another thing. Meaning that, so this function composed with f will take a morphism from A to H, where f is from B to A. It'll take a morphism from A to H, and it'll give me a morphism from B to H. Because I've got B to A, I've got A to H, I can get B to H. Does that make sense? Okay, cool. So, right, so this is just my comment about handlers. All right, so there's one more class of examples that I want to look at. So, we've got a monoid, M, and we're looking at, so we can think of M as a one-object category. What does it mean to have a functor from this M to set? So, all right, how would we go about defining such a functor? Well, M only has one object, so we'll get out a set, which is just f of star. And given any morphism from star to star, or alternatively given an element of the monoid M, we'll get a function that goes from x to x. So this is sort of like you're taking M and you're manipulating elements. You're using M to manipulate elements of x in some interesting sense. So it also preserves identity and it preserves multiplication. So I'm going to define something a little bit similar, and then we'll see how it's really the same thing. So I'm going to say what an M module is. So if M is a monoid, a module for that monoid consists of a set X and one of these a function that takes an element of the monoid and an element of X and returns another element of X. And you call this guy the action of the monoid M on X. You want it to be, that the identity element of the monoid acts like an identity function. So if you do this one applied to X, you get X. And given any two elements of the monoid and an element of X, if I do multiplication and then act on X, it's the same as acting on X with the second guy and then acting on it with the first guy. So to give you sort of an intuition for how to think of this, you can think of X as being sort of like a vector space, and that this triangle function is specifying a way to do scalar multiplication, where you can multiply an element of M by a vector X. It's not quite a perfect analogy because you can't add these vectors, and maybe it's not. Maybe if multiplication in M isn't commutative, then this multiplication isn't commutative either. But it still kind of looks a little bit like that. You can if you multiply any vector by 1, you get the same vector back, and if you multiply it by n and then you multiply it by m, it's the same. Yeah, if you multiply by n and then multiply it by m, it's the same as multiplying it by m times n. So the notions of an m, yes? Which arrow? It's not quite a category. This is, you should read this kind of like a type signature. You should think of this as it takes an m and an x and it returns an x. So you could think of it as like a curried function, or you could think of it as uncurried function, or you could look at this as m cross x to x. Either one works. But But you can sort of think of it as taking m and lifting it into the set of functions from x to itself. So that does make sense. So it turns out that m modules and functors from m to set are exactly the same thing. So, so we have a set, an action, and it obeys some laws. So the set is just f of star, and the action of m on x, well, we want a function from x to x, so f of m is going to be that, and we apply it to our element x. So so f of m is a function from so if you think of m as being your category, m is a morphism from star to star. So f of m is a morphism in set from x to x, so it's a function from x to x. So in particular, you can feed it the value x, and you'll get back another value x. If you do the identity, if you take the identity element of the monoid and act on x with it, well, the identity is just id star, so it's just f of id star of x. Since f maps identities to identities, you get id x of x, and so you just get x out. And similarly, you get this kind of longer equation where you have, if you take a composition of m and n and apply it to x, well then you can split the composition out into f of m compose n is f of m compose f of n, and then I apply that to x, so I just sort of wrap all this up, and then I have f of nx is just n triangle x, and f of m of that is m triangle that. So you can think of these functors as being sort of these mathematical objects in their own right. You can think of them kind of like vector spaces. So we might want to ask, what are the morphisms between two of these m modules? This is where we get into natural transformations. So if I've got two functors from a category C to a category D, I want to ask, what does it mean to have a morphism between these two functors? Which is kind of a little bit weird since functors are morphisms themselves, so this is like a morphism between morphisms. So the idea is, if I've got an object x in my category C, then, well, f gives me an object and g gives me an object. So a morphism should, give me a bunch of morphisms from f of x to g of x, one for every object. So, okay, let's take that as our definition of a morphism of functors for a moment. See what the problem is. All right, so I'm going to define, I'm just going to use things in Haskell right now. So I'm going to define a morphism from the list functor to the maybe functor, and here's what it's going to do. If I give it an int for int, well, I need to give a function from list of int to maybe int. I'm going to pick just compose with sum. If I do it a string, I need a list of string to maybe string. Well, I don't know what to do with that. I'm just going to do const nothing. And then I, keep defining these, and I do it once for every type. It'll take me a long time, but I've got, infinite amount of paper and disk space, so whatever, it'll work, right? So the problem is that, clearly these are doing really different things. Like, this one will give you a just, and this one will give you a nothing, and it's like there's nothing in common with them. So the problem with this definition is that you need to remember the morphisms in your category C. So let's say I've got a morphism from x to y in my category C. So, I get a morphism from f of x to g of x from my natural transformation. I get a morphism from f of y to g of y. I'd like these guys to be related somehow. Like, they can't be like completely different things. One of them, you can't have one of them be, just sum and the other one being const nothing. So how are we going to turn these, how are we going to connect these things together? Well, f and g are functors. So I take my morphism from x to y, and so I'll get a morphism from f of x to f of y, and I'll get a morphism from g of x to g of y. And now there's, something sort of connecting them together, but we don't really know entirely what that means yet. That's what I'm going to do next. So now we define it. Natural transformation from f to g. So given an object in x, I'll give you back a morphism that goes from f of x to g of x. And I'm going to sort of use this subscript x notation. People like using Greek letters for natural transformations for some reason. So if I've got a morphism from x to y, I say the following diagram commutes. And then people look at me and are very, very confused with what that means. What does it mean for a diagram to commute? Here's what it means. So here's the basic intuition here. If I've got, the idea should be, if I've got a diagram like this, then no matter where I start and where I end, any path I take from start to finish should be the same. So in particular, this means if I go down and then I go across, it should be the same thing as if I go across and then down. So if I wrote that out as an equation, I would say, well, g of f composed with eta of x is the same as eta y composed with f of f. So we want this, so that's what it means for this diagram to commute, is that both paths are the same. So some examples of natural transformations. So if I've got list, again, list and maybe, I can make a natural transformation from list to maybe, and let's call it safe head. What does it do? Well, you give me the empty list, I'll give you back nothing. And if you give me something with a head and a tail, then I'll just give you the x. I'll give you the head. So if I've got any function from a to b, you could prove that if I do fmapf.safehead, I get safehead.fmapf. Or another way to look at it, which I think is a little easier to understand, is we can say that this diagram commutes. So I've got list of A and list of B, got maybe A and maybe B. So if I've got a function from A to B, I can map it over the list, and I can also map it over the maybes, and I can either take the safe head at the beginning, or I can take the safe head at the end. And the result is going to be the same, because map is going to keep the same structure of the list. It's going to, the head is always going to be the same if it exists. So either way I go through this, it's going to give me the same result. So you can sort of think of a natural transformation as giving you a way of saying, at any point, if I've got a sequence of functorial computations, and I want to get at some point from one functor to another functor, this gives me a way of saying, well, I'll give you a way of doing that, and you can do it whenever you want. You can do it at the beginning, you can do it at the end, and the result is going to be the same. You can do it somewhere in the middle, it'll be the same. All right, so back to M modules, really quickly. So we've got a functor from M to set. We want to look at what's a natural transformation between two of these modules. So there's only one object, so all we need is just one function, f of star to g of star. And given any m in star to star, we'll want to have this diagram commute. All right, so what the hell does this mean? All right, so I'm going to sort of go back to the other way of thinking about modules as being a set with an action. So if I've got x and y are two of these modules, then I call something an M-linear map. If I have a function that goes from x to y, and given any scalar m, f of m times x is m times f of x. So this is, again, sort of like linear transformations in linear algebra. You have it, if you multiply it, you can either multiply it inside the function or outside the function. It does the same thing. So in other words, you have a commutative diagram. So given any element m, I can first go from x to x by acting with m, and then I can go from x to y using f, or I can go from x to y using f and then multiply with m and y, and the results are going to be the same. Now, bam! So this is exactly the same diagram. I just renamed everything. You know, f of m is just m triangle x. G of m is just m circle y. These guys are both x, these guys are both y, and eta star is just f. So, in conclusion, linear maps are just natural transformations, and natural transformations are linear maps. Given you know, 3 functors going from C to D, I've got a natural transformation from f to g and one from g to h. I can compose them. It's fairly straightforward. I just, you know, the composite at a particular object is just the composite of the individual morphisms for that object. And the diagram commutes because both sides commute. So it turns out that composition of natural transformations is associative. And there's an identity natural transformation from any functor to itself. This should start to sound familiar by now. I get a category. So given any 2 categories C and D, there's a category of functors from C to D. The objects are the functors and the morphisms are the natural transformations. And you might see this notation with the brackets, or you might see d raised to the c power because, you know, maps turn into exponentials if you know, stare at them long enough. All right, how am I doing on time? I have enough time to state the UNA dilemma. Okay, so let me just do one thing real quick. So any monoid M can be thought of as a module for M, right? Because you can multiply. And, you know, it's associative and has a unit, so it works. If I've got another module, I can look at all of the M linear maps from the module M to the module X. So if I've got a linear map, then, you know, given any element M, well, M is just the same as M times the identity in M, because that's just how multiplication in monoids works. And since F is linear, I can pull the multiplication out into the multiplication in X and just have M times F of the identity. So let's look at what I did here. So I said for any M, F of M is entirely determined by F of the identity and, you know, how the action works in X. So this is kind of like in linear algebra. If you've got a function from, if you've got a linear map from the real numbers into a vector space, it's entirely determined by where you send the number 1. Because scalar multiplication is just going to, you know, scale it up and down in whatever direction. So this is a theorem, which is, I'm going to call Cayley's theorem, even though Cayley's theorem's for groups and these are just monoids. So if M is any monoid, then I have M itself as an M module with action given by multiplication. And if I have any module, then there's an isomorphism between the module and the set, or the module as a set, and the set of linear transformations from M to X, because one of these is determined entirely by where it sends the identity, and entirely determines where it sends the identity. So, in particular, the linear transformations from M to itself is isomorphic to M. Even though, you know, if you look at all of the functions from M to M, there's generally a lot of them. So, for instance, if you take list of A, there's a lot of functions of type list of A to list of A for a particular A. But there's sort of only so many linear ones that, you know, preserve concatenation and empty list. So there's a neat little application of this where you say, okay, well, I'm going to take, let's say I've got a monoid that has where, you know, maybe multiplication isn't super efficient. Maybe maybe it's like lists where it takes more time to be left associated than right associated. Well, I can turn each element in my monoid into a function from the monoid to itself. And then I can compose all these functions together. And then I might get something more efficient by applying it to the identity element. And this is basically exactly what difference lists are. Is they say, I've got a list, I've got, you know, I build up a bunch of list appends by turning each list into the function that takes any list and appends this list onto it. And, you know, the result is, and then if I take all of those and I apply it to, compose them and I apply it to the identity function, I get back the whole list. And it ends up being more efficient through magic. So, it turns out this is the module we described is exactly the Hom functor that we talked about earlier. So it just, the set of elements is the set of elements, and you know, the action is given by multiplication or composition depending on how you think of it. So since linear maps are just natural transformations, we can characterize it in exactly the same way. And in particular, you know, since eta star of m is just eta star of m composed with the identity, it's equal to f of m of eta star of identity of, you know, the identity. So, you know, you multiply by m and then you take your function. It's the same as taking your function and multiplying by m. So eta star is entirely determined by where it sends the identity. So there are exactly as many natural transformations from Hom star f, Hom star blank to f, as there are elements of f of star. This is kind of neat. This is like just, you know, a regular old set that, you know, you know that you might work with. This is like some like huge space of functions that natural transformations between functors, between morphisms, and this other thing that, you know, is generally much more complicated to understand, but it just turns out to be the same as this other thing. So we can do the same trick for an arbitrary category, where for an object R we have this functor, and if we've got another functor we can look at the natural transformations. And, you know, by naturality we know that, you know, if I have Hom RR to Hom RA and f of R to f of A, then eta of R and eta of A need to make this diagram commute. So, in particular, if I follow the identity function, if I take the identity from R to R, I turn into f, and then I take eta A of f. That's the same as eta R of the identity, and then, you know, just f map over it. So, what eta does on every single object is determined entirely by what one component of eta does on one element of Hom RR. So we've just proven the unit lemma. So if I've got any category C and any object, then I can, and I've got any functor from C to set, then I can look at all of the natural transformations from this Hom functor to f. The unit lemma says that it is isomorphic to f of R, which is just a set. So in a philosophical nutshell, if you want to know what something is, you only need to know how it behaves. And if you want to know how something behaves, you need to know what it is. That's the Oneida lemma in a nutshell. Now I've got a bunch more things talking about the contravariant Oneida lemma and the Oneida embedding, but it's a bit, I'm already over time, so these slides are going to go up at some point probably. In the meantime, I have, in case, you know, this talk has piqued your interest and you want to learn more about category theory, there's a few things I'd recommend reading. One is, there's a lovely free online book by David Spivak called Category Theory for Scientists. it is much better. It is a very nice basic introduction. Goes through things probably a lot slower and cleaner than I did today. And it actually does something very neat where it shows that a category is exactly the same thing as a database schema. If you want to know more about that, we can talk at the bar. There's a group of I think graduate students at the University of Sheffield in England called the Catsters, who do YouTube videos about category theory. They're very good. If you want to get a little bit more in depth, there's Saunders McLean's Categories for the Working Mathematician, which is, sort of, he's the guy who invented category theory. So it's a pretty good book, but it's very, very mathy. And if you really, really want to have your head explode, you can go and visit the NLab. I promise it will make your head explode. All right, thank you.